Okay, welcome back to ME2002, also known as your favorite class. Scheduling coming up soon. I was just having a conversation with some of the folk in class here today. I'll be teaching mechanics and materials next quarter if people are interested in taking that with me, if you like my style. Otherwise, if you don't like my style, take it with someone else, okay? So that's your mechanics and materials 1 class. Right. Today's topic, rotating coordinate systems. Do I have my thing down? I do have my thing down. Rotating coordinate systems. Homework 5 is due today. Hopefully you got that in. You're all crystal clear now on one-dimensional particle motion and a slight little flavoring of 2D particle motion. And homework number 6 and simulation 2 coming soon. Simulation 2 will probably be on 1D motion. And homework 6 will be rotating coordinate systems, which is what we're going to start today. Okay, how are we doing? We like the meme today? Yes, calculus. Almost done with Calc 4, most of you, but you already learned double integrals anyway, so what do you need to go to Calc 4 for? All right, but you got thermo and fluids coming to get you. Rawr. Okay, I'm guessing you guys are probably going to be scheduling pretty soon, and I think you actually schedule thermo for the spring, don't you? Is it thermo? Yeah, right. Elisa's shaking her head. We only got 3 people here in person today, braving the elements. Man, 3 is better than 0. Nick almost got a personalized lecture, and then Elise and Mr. McDonald showed up, so. Okay, right, enough chit chat. Let's get down to business, as they say in Mulan. That's what you guys are all thinking, right? Mulan, your favorite movie? It's actually pretty, I guess it's debatable, but some sexist undertones to that movie, possibly. Right, so let's avoid that landmine, and let's get down to business. Just the song, not the movie. All right, so today we're going to talk about rotating coordinate systems, and I've sort of been prepping you for a bit of this, but now we're actually going to see the math behind why we needed to keep track of our derivatives so closely. Hey, Rufus, Doofus, keep it down. All right, they're discussing Mulan. Must be a very intense conversation. Right, Eddie Murphy was the best actor in that movie, by the way. Okay, so we're doing rotating coordinate frames today, and we've sort of been prepping for this up to now with talking about derivatives and making sure we're keeping track of derivatives appropriately as we do them, specifically vector derivatives, because now we're going to see that our unit vectors are not actually sort of irrelevant when it comes to taking the derivative. They're actually going to be important because now the unit vectors that sort of point in the direction of interest are going to be sort of rotating as the particle moves around and rotates. So today, rotating coordinate frames. And so we're kind of continuing our rectilinear motion conversation. Motion not in one dimension, so along a curve in either 2D or 3D. And let's recall quickly that the velocity of a particle as it's moving is tangent to the path. So that's important here. Okay, and we know that from conversations of our curvilinear motion from last week. So because velocity tends to be tangent to the path, we might consider a situation where we're not defining a fixed coordinate system in space like you typically do, but instead, maybe we define a coordinate system that has one of its axes in the direction of the velocity at all times. So what I mean by that is let's define a coordinate system where one of the axes is in the direction of the velocity always. So sometimes it's helpful. I don't want to say helpful, useful to define a coordinate system, or let's say a unit vector, which constantly points in the direction of the velocity along the tangent to the path. It's just mirrors at like 1,000,000 degrees in here. Man, it is freaking warm in here. All right, so we're going to call this the tangential unit vector, and we're going to denote it with a little bit of weird language, but it's going to get an E hat T. Call this the tangential unit vector. For obvious reasons, because it's tangent to the path, clearly. And we denote it as E hat T as such. All right. So if we want to like consider a picture of this, here you might have your traditional coordinate system. It's like X, Y. And we'll say that this is like fixed in space. Maybe we give this a Z also for completeness. Here's your origin O. And again, we have some particle that's moving along some curved path. Okay, this is the path of our particle. And here we are at point P. Everything we've done so far, we've sort of like located this particle in space using our traditional position vector, which is like this guy here, this R hat. And we know in our fixed coordinate system that the derivative of that position vector with respect to time will give us velocity, and that the velocity will generally be tangent to that path. So we know that we're going to have a velocity vector, something like this, which we know is dr dt. Right. Now, with our new definition of our unit vector E hat t, we could also simply write this now as this is the magnitude of the velocity, whatever it is, in this new unit vector direction E hat t. Right? So we're now going to say that there's this unit vector that exists. I'm going to sort of draw it up here. It's generally in this direction. A unit vector, remember, magnitude of 1, pointed in a certain direction. So it's basically a vector of magnitude 1 that helps you define a particular direction. You're used to probably I hat, j hat, k hat. Obviously, those are vectors of magnitude 1 that point in x, y, and z. But here now we're defining a unit vector that points in the direction of velocity. Here is E hat t. All right, so now we have to consider, all right, we want a full coordinate system that sort of defines a full basis, not just one particular direction. So if we want a full basis, we need another basis vector to sort of like fully define our two-dimensional space. And then we'll need a third basis vector to fully define our three-dimensional space, okay? So to do that, let's consider motion of this particle and help us sort of define another sort of piece of our basis vectors, okay? So let's move this, and we're going to move to P prime. Okay. And let's say after some time later, we have a new unit vector that points in the velocity that P prime is moving, and we're going to call that E hat T prime. So here my velocity has changed now. Let's call this V prime. And I have a new unit vector which sort of points in this general direction, which is E hat T prime. Okay. So now I want to know, how is that unit vector changing with respect to time? Because I'm concerned about how my velocity is changing with respect to time. I want to know how that unit vector is changing with respect to time. And now, because this unit vector is sort of like riding along the particle and generally like changing its position as it sort of like moves through space, the time derivative of this particular unit vector is not going to be equal to 0. The time derivative will now have some importance, okay? So now, time and space derivatives associated E hat t are not 0. And we must discuss. Okay, so let's dive in on this math a little bit more. Okay, let's first talk about sort of a positional derivative of this unit vector, and then we'll use that as a proxy with the chain rule to get us the time derivative of this unit vector. A little strange, but just follow me on this. Okay, so here let's talk about the angular derivative of a unit vector. And specifically the unit vector here, E hat t. Okay, so let's consider the situation we just had, where we had this sort of unit vector that was changing from, maybe this general direction when I'm at point P to sometime later this general direction when I'm at P prime. All right, so let's draw E hat t and E hat t prime emanating from same point. Okay, so here we are. And we have E hat t. Okay, that would be like the direction of the velocity of P. And sometime later, this guy is rotating and changing to another location or another position. Here we call E hat t prime. All right. I know the magnitudes of these vectors are what value? Rhymes with fun. 1. Okay, good. All right. And there's an angular distance between them, sort of how they're changing, which I'm going to call just for now delta theta. Okay. My question is, what is the change of this general position vector as it moves from point P to P prime as a function of position, as a function of rotation? Okay. So let's be clear about this. Vectors have magnitude. Of 1. And angle between is delta theta. That's the amount that my angle has changed as I'm riding on this particle from location 1 to location 2. Okay. So my question is, all right, what is the change of this unit vector? And so what I want to know is, as I'm going from sort of E hat t to E hat t prime, what is this vector here? The change in E hat t as I'm moving from location 1 to location 2. Okay. What can I sort of determine about this particular vector? Okay. Well, let's start with this generally being a triangular shape. Here. Okay. I know that the length of this is equal to 1, the length of this is equal to 1, and I know the angle between them is this delta theta. So if you remember back to your geometry class, if you have a triangle and the side lengths of 2 edges of that triangle and the angle between, you can get the length of the opposite side using law of cosines. Sorry, it should be delta E hat t. Okay. So you can work that if you remember your law of cosines. It's very similar to Pythagorean theorem. Maybe you remember that, maybe you don't. But you could work your way through this where, you know, A is 1, B is 1, right? Because these are the side lengths of this particular triangle. Your angle C here is delta theta. You could come up with a situation after some simplification that and actually some trig identities here, that the magnitude delta E hat t is 2 times the sine of the half angle delta theta on 2. You want to work that as an exercise, that's cool. If you're going to exercise this, you'll want that may be useful on your next homework. Okay. Okay, so now we have the magnitude of this particular vector, and what the heck is this? 2 sine delta theta on 2. Okay. Well, let's keep moving. We know that it makes that motion from sort of this delta E hat t to this delta E hat t prime by moving through that angle delta theta. So let's normalize by that and see what happens. On this angle that we sweep through here will be 2 times the sine delta theta on 2 divided by delta theta, right? Why is this particularly powerful? Because this is starting to look a lot like a positional derivative, right? The change in a particular unit vector over the change in some angle. This is like the derivative of the unit vector with respect to the angular position theta. That's what we're trying to get. This is going to help us to get the derivative of the unit vector with respect to time through the chain rule in just a second. Okay. You can rearrange this by moving the 2 to the bottom. Looks something like that. And now the idea here is, again, this looks a lot like the derivative of a unit vector with respect to an angle. So in differential, take limit as the change in the angle becomes very small. I want to know if I have a very small change in my angle, what happens to this vector that we've created that moves from E hat t to E hat t prime? Take limit as delta theta goes to 0. Okay. So here, this becomes the derivative E hat t with respect to the angular position theta. Here, this is the limit as this angular position goes to 0 of this whole expression. Anyone happen to know this this derivative or this limit? What's the limit of sine x on x as x approaches 0? Bam, she knows it. Elise, crushing it like a grape. She took it to school today because she's at school. Okay. This is like the derivative or the limit of sine x on x. So think about this. Limit as x goes to 0 of sine x on x, right? This is more or less exactly what you're looking at, okay? Because you could think of this as the limit as delta theta on 2 goes to 0. Same darned thing, okay? So the limit as x goes to 0 of sine x on x. Unlike in Mean Girls where the limit does not exist, this limit does exist, and it equals 1. Anyone get that reference? The limit does not exist. The limit does not exist. Okay. Interesting. So what we end up with is that this particular derivative here, I guess this should be a sort of a magnitude here because we have to make sure that this is a magnitude. This is a little bit more mathematically correct. Okay, it's equal to 1. So what does that mean? All right, well, if we take the angular derivative of this particular unit vector as that angular motion is approaching 0, that we have a vector that is created of magnitude 1. A little bit strange to think about, okay? So what we saw with our math is that, we go back up to this triangle here. As this angle delta theta goes to 0, the magnitude of this particular guy, normalized by this amount, goes to 1. Wouldn't be intuitive by sort of like thinking about that, but that is the case, right? So, one other thing we need to know. Also, as this angle goes to 0, the angle between delta e hat t and delta e hat t goes to 90 degrees. And this is sort of obvious to see. If you think about two vectors that are, God, my pen keeps falling down. Okay. So what I'm talking about is sort of this angle here. Yes? Okay. So as e hat t and e hat t prime are closing in on each other, imagine them very, very, very close to each other, then the angle between e hat t and delta e hat t would be perpendicular, be 90 degrees as they approach each other. All right. So let's now give some definition to this delta e hat t, okay? So the angular derivative of a rotating unit vector with respect to the rotation angle theta let's say in plane rotation angle is a unit vector of magnitude 1, which we proved, which is 90 degrees from the original unit vector. Which is itself a new unit vector. A vector of magnitude 1, 90 degrees from the original vector. we call this normal unit vector. This is 90 degrees from E hat t, pointed towards the center of curvature. Okay, so since I'm curving a particular direction, it's important to define that this normal direction is pointing towards the center of curvature. So, I'm taking this vector, I'm moving it here. My angular rotation is generally this direction, so my unit vector is going to end up pointing in that direction as well. This is towards the center of curvature. Okay. What does this actually look like sort of pictorially? So here's your traditional XYZ. We're moving in space on our curve here. Here's my particle, P. My position vector that locates that particle. And the velocity of that guy. Okay. So overlaying right on top of that velocity is the tangential unit vector here. And 90 degrees from that, pointed towards the center of curvature, is the normal unit vector here. C E hat n. Oh, that's not 90 degrees. Come on. It's a little better. Where we note another interesting tidbit. Who's got this one? The derivative of the normal with respect to theta. Where does that point?
Is that just the negative original velocity?
Excellent. So I got it in my ear. This is going to be negative the original direction, which I think he means E hat t, which is correct. So some interesting sort of properties with these derivatives that are like riding on the particle. All right. So more information on normal and tangential vectors. Normat, Jesus. Normal and tangential unit vectors. Okay, so a little bit more information on these guys here. These guys are a set of basis vectors in 2D, meaning since they're like 90 degrees with each other, they can sort of take the place of like I and J if you're sort of working in a two-dimensional problem, right? So you guys talk about basis vectors? Probably not until you get to like vector math, right? Like a senior level vector math. Yeah, okay. I'll use the proper language anyways. Unit vectors. E hat t and E hat n form a basis in 2D. This is similar to it. I and j. Right? If you got a vector that's in space, yeah, you could you could define it in terms of I and j components if you have that coordinate system. But also if you had some alternate coordinate system, you could also fully define that vector in terms of E hat t and E hat n. Right? Okay. Their axes are referred to as normal and tangential axes. Obviously. Like I said, it's similar to I and j, but they ride on the particle. With E hat t, always in direction of velocity. Meaning that in this coordinate system, you can always define your velocity vector in this way. Sorry, handwriting got a little sloppy there. So what do you do about the third direction? Well, the third direction, we're just going to define a third direction using sort of the right-hand rule. All right. So in 3D, you need another unit vector. Okay. We call this the binomial unit vector. E hat b. The direction of E hat b is going to be out of the plane containing E hat t and E hat n. And we're going to use sort of the right-hand rule starting with E hat t, crossing to E hat n to give us E hat b. And so this binomial unit vector given by E hat t crossed with E hat n with right-hand rules applicable. Okay, last couple things. Plane containing E hat t and E hat n is called the osculating plane. And E hat b always perpendicular to osculating plane. Okay, so what are we doing here? We're defining for ourselves a new coordinate system, basically. And this coordinate system, unlike your traditional XYZ coordinate system, is no longer just fixed in space. It's moving on your particle. Okay? So this is useful for a number of reasons that we're going to see shortly, but for now, you need to understand that the derivatives of the unit vectors which are associated with this new rotating coordinate system are not zero. Okay. Let's consider kind of the full picture of everything that's happening here. And let's really give it like a three-dimensional view if we can. All right. Here we go with XYZ again. Doesn't really matter how it's defined. I think I might have defined it a different way before, but the point is the same. And let's say we have some wonky three-dimensional path that this thing's going on now. It's not just contained in a particular plane. Do the best you can to like imagine that this is like a three-dimensional path. I know it's hard to like draw a three-dimensional path sort of on a 2D piece of paper, but let's just go with it, okay? All right. At any particular location, you could think about where the particle is, what the tangent to the path is at that particular location, and where the center of curvature for that particular curve might be. So if you thought about the particle being, let's say right here, well, if we're moving sort of this way along the path, then the velocity is going to be in this direction. So here's your E hat t at that particular location. And pointing to the center of curvature, here would be E hat n. The center of curvature at that particular location looks like it's sort of pointing inwards. And if I were to think about E hat n crossed with E hat t, my thumb would sort of stick sort of backwards. And if this is like the plane that contains E hat t and E hat n, then the binomial sticks out of that plane in sort of the backwards direction. Okay, where that blue is the osculating plane. Okay. Later down the line, your particle might be here, still moving in this general direction. Tangential. But now our sort of curvature is sort of flipped on us. And now we're pointing inward a little bit. Okay. And here the outward to the plane. If this is our plane here. Here the outward to the plane, E hat t crossed with E hat n is going to be something like this. I know it's not the cleanest. Maybe I give myself a little space here. Okay, I know hard to draw in 3D, but I think it's a good general idea or perspective. No, it should be E hat n. All right, so those are some nice, sort of nice as best as I can do with Pictionary, my Pictionary skills. All right, so that's great that we have sort of a nice new coordinate system. Now let's talk about kinematic relationships with this guy finally. Kinematic relationships. All right, velocity is here. Yes. How do we get the acceleration if we have the velocity? What's that? If you have velocity, you want acceleration. You, with respect to? Yeah, with respect to time. We've talked about the angular derivative, which is a positional derivative. It's not deliberative, it's DiGiorno. Okay. So I got some chuckles on that one. All right. So for acceleration, take time derivative. Okay. So here we have the acceleration is dv dt. Well, we can expand this with our new sort of definition of the velocity. It's the magnitude of the velocity along E hat t. It's time for chain rule, boy. All right. So here, this is like u and v. So u dv plus v du. So here we are going to have derivative of the first times the second plus the derivative of the second times the first. So here we have the derivative of the magnitude of the velocity, dt, along e hat t. It's the derivative of the first times the second, plus the first times the derivative of the second. Interesting. So we might think about identifying some of these terms at this point. This guy here, the derivative of the magnitude of the velocity with respect to time, particularly in this direction. Right? This here is the acceleration of the particle in the tangential direction. So this you might see as the acceleration in the tangent direction along e hat t, where that at there is a scalar. It's the acceleration in the tangential direction. Think of this like the scalar of the acceleration in x direction along I hat when we do our rectangular coordinates. Right. This obviously is magnitude of velocity. This here, not 0, okay? This is the time derivative of the rotating unit vector. We've talked about the angular derivative. Now let's talk about the time derivative. So remember when we did like our rectangular coordinates, we saw something like di dt, okay? And every time that we saw something like di hat dt, we said that that was 0, because if you have a unit vector that's fixed in space, you take the time derivative of that thing ain't changing at all with respect to time, right? But now you've got this, you know, tangential unit vector that's floating on this particle and pointing every which way, and it's going crazy. Okay, that's definitely changing as a function of time. You can't just say that that's going to be 0, right? So you gotta deal. You gotta deal with that. Okay. No longer true. Rawr. Okay. Let's give you a break here, and we'll come back and we'll do the time derivative of this positional unit vector. 4:45 we'll give you to, let's say 4:55. So a little less than 10 minutes. Be back in 9 minutes. my girlfriend took a picture of our dog. Kind of a troublemaker. I learned something interesting on the weekend. You know how we use a base 10 numbering system? There's an ancient language that used a base 10,000 rating system. It was unclear, a Mesopotamian society, right? And so they had symbols that represented one single symbol that could represent all numbers from 1 to 9,999. Yeah. Yeah. It was almost based. It was almost based in like a base 10 system. So the idea was it has this like tree that's like the base. It's like a straight line. It's like interesting. Instead of lost that right on the right of the whiteboard. This would represent 0. Okay. And then if you're working in this quadrant, that represents like the ones place. Here represents tens, here represents hundreds, here represents thousands. Okay? And each different, way that you could draw in those 4 coordinates would be representative of like a base 10 digit. Okay? So you can think of this as like 1. Okay, this is like 2. Okay. This is 3, this is 4, this is 5, something like that. Okay. And so here it'd be like 5 represented in this way. This would be 15, right? Thought about that. And then maybe something like this is 215. And so they had a way to represent every number from 1 to 9,999. If, like, let's say this represents 9, okay, now you have 9,215. Okay. And they could represent all of the numbers from 0 to 9,999 using one symbol.
Not bad.
What's that?
That's not bad.
No, it's not. What's that?
Yeah.
Imagine doing like multiplication with those symbols. Oh my God.
It kind of like you're escape trying to understand what that's supposed to be.
Yeah. I mean, like, if you worked with it enough, you would understand it, I think.
Mhm.
It still has a base 10 feel because it's still sort of based in a base 10 system.
Mhm.
So each one of those quadrants is like a base 10. I thought that was like a interesting or like a unique thing. Maybe I'll do all my notes from now on in that language. Yeah. You have to get out like the key to figure it out. Oh, what is this stick pounds? I don't understand this. Okay, let's get back to it. Okay, where's my pencil? There we go. And by pencil, I mean electric pencil. And by electric pencil, I mean stylus. All right, 455-ish. It's actually 454. Oh, there it goes, 455. Let's get back to it. All right, so we're interested in the time derivative of this tangential unit vector. Remember, this is a unit vector that sort of points in the direction of the velocity. Now we want to talk about a time derivative of that particular guy. So let's get on with it. Time derivative. Okay, so we want this dE hat t with respect to time for our acceleration expression. How can we do this? I don't know. Don't ask me. What do I know? Oh, okay. Well, dang it. I got to know. All right. Now, this technique's a little tricky, but what we're going to do here is we're going to employ chain rule using a series of derivatives that we can physically understand to help us get to this final derivative. So let me show you what I mean. We're going to employ. We're going to employ it. We're going to pay it minimum wage. And we're going to not give it healthcare. Okay, no. Employ chain rule. You will get paid $7.25 an hour and like it. All right. Employ the chain rule. Where here we say that this particular derivative can be broken up into things that might be a little physically, we might be able to understand a little bit better. The first being a piece of information we already have. The angular derivative of this guy, which we know, which is? He's already given up. All right. E hat n. Good. Thank you, Miss Elise. She's always coming through for me today. She's making you guys look bad. Okay? Making you guys look bad. All right. But this is, not accurate as written. We need more information here. So we need something to balance out that theta. Sounds pretty good to me. Here. And let's talk about what each one of these things are. if we can sort of figure out what each one of these particular terms is here, sort of physically in terms of things we understand, life will be better. Where S is the particle path. All right. Everything else here is pretty well defined. All right. So we got to look at each one of these little derivatives separately and see what we can sort of get from them. So let's consider a picture. Lots of pictures these days. Here we have like your XY coordinate system. And let's say that our particle is moving along this path. All right. And it moves like normal from P to P prime as such. And let's say that we're moving along a circular path. And this particular circular path has our center of curvature, maybe up here. Let's call this C. So moving from P prime along circular path. With center of curvature at point C. Okay. What does that mean? Okay, circular path, center of curvature at point C. That means that the distance between the center of curvature and these particular points is known and understood. And we will call this, since this is the center of curvature, typically we denote that with a rho. Row your boat. Okay, so here path length. The radius here is rho, and path length from P to P prime, we'll say is delta S. So what I mean is this length here, this sort of total arc length, is the arc length delta S. This is different from sort of like the direct distance between P and P prime, which we talked about before in this class, earlier in this class. Let's also say the angle we sweep through is delta theta. Okay. That generally is this angle here. Okay. With equations for the arc length of a circle, you can come up with a relationship between rho, delta theta, and delta S. And that is this total path length that you travel is the radius of curvature rho, delta theta. All right. We want to take the limit of this as delta theta sort of goes to 0. So we're going to rearrange and say that in this particular situation, we have delta S on delta theta. Is this right? Yep. This is rho. So we'll take the limit here in the differential and say generally that ds d theta is rho. Change in this position with a change in angle is rho. Or if we go back up and you look, we actually want like the inverse of that. One on rho. Where rho is the radius of curvature at that particular instant. Sort of the next bit in our equation here. Okay, last little thing we have to worry about is this here. That one's pretty straightforward. The change in the total path over time. This here is the speed. We don't have any direction. This is the total change in the path over time. So as you know, you take this in the differential, how much are you changing your position, or how much are you changing your path over time? This is the magnitude of the velocity, which is the speed. So the differential change in path length over the differential time is the speed. It's like meters per second, basically. So altogether, we have the derivative of our tangential unit vector with respect to time was something like the derivative of this guy with respect to the rotation angle theta multiplied by the derivative, with respect to position. The derivative of the angular rotation with respect to the change in the path length multiplied by the change in path length with respect to time. All of these things now we know. Here, this is E hat n. Here, this is 1 on rho. And here, this is the magnitude of the velocity. Put it all together. This is the magnitude of the velocity divided by the curvature at any particular time in the direction of the normal. Interesting, interesting, interesting. Bet you probably wouldn't have guessed that. I wouldn't have. The derivative of the unit vector in the tangential direction with respect to time is the magnitude of the velocity normalized by the radius of curvature times the normal. What? How is that a thing? Okay. It just doesn't really make a lot of sense until you do the math and you're like, okay, I guess that's what it is. All right, so back to acceleration then. Remember that we had acceleration is the derivative of the velocity with respect to time, which we wrote as the derivative of the magnitude of the velocity in E hat t Or as we saw, this was this guy plus the first times the derivative of the second, which we now have an expression for. So finally, this acceleration. We'll notice here that we have magnitude of the velocity as part of this expression. So we're going to end up with two of those magnitudes of the velocity normalized by rho and E hat n. So this is the magnitude of the velocity squared, normalized by the radius of curvature, all in the normal direction. Yeah, baby! There you go. You may see it written as this. Useful. Where obviously the tangential component of the acceleration is the change in the magnitude of the velocity with respect to time. And the normal component is the magnitude of the velocity squared, normalized by the radius of curvature at that particular instant on the curve, rho. I'm going to write it here. And I'll draw a picture. Typical coordinate system. That's nice. All right, here's our picture. Got our particle, bam. I want to draw the acceleration components of this particular particle P. I can do that here. The acceleration in the tangential direction is given by AT. This has a magnitude, which is the change in the magnitude of the velocity normalized by time. This is specifically in E hat t. And we also have our normal components of our acceleration, which point inwards towards the center of curvature. It's the magnitude of the velocity squared divided by rho. This is useful because let's say you have a particle traveling on a circular path. Well, if you know kind of the velocity of that particle on the circular path, you can easily define some of these components, like what is my acceleration in the normal direction, what is my acceleration in the tangential direction at any particular time. You can also easily define the velocity. It's just the magnitude of the velocity in the direction of the particle, or all tangent to the path in E hat t. And that can allow you, in some situations, to easily define the position if you're, for instance, writing things in as a function of time. All right. Now, let's see an example problem where we actually use this stuff. So much talky, so much mathy. Let's do some realistic applications here. Okay. Leadfoot Larry, my favorite friend. Actually, should just be Leadfoot Dr. Hart, what it should be. Traveling on a curved section of a highway, and this particular curved section of the highway has a radius of curvature of 2,500 feet. Leadfoot Larry's going 60 miles an hour. Man, he's cruising on that curve, baby. Slams on the brakes, causing the vehicle to slow at a constant rate. He's very good with his braking to slow at a constant rate. After 8 seconds, the speed of the vehicle is reduced to 45 miles per hour at a constant rate. Neglecting gravitational forces, determine the acceleration of the vehicle right when the brakes are applied, and the g-force experienced by Larry at that moment. Larry's got a lot of G's. Another 30 seconds or so. My old pal Leadfoot Larry. Or is it Leadfoot Larry? Maybe he's just a very good dancer. I'll just give Larry the benefit of the doubt. Just a very good dancer. Leadfoot Larry. He likes to lead. Okay. Let's tackle this bad boy. So what are we asking for? We want the acceleration of the vehicle right when the brakes are applied. All right. Hey. Get back here. Okay. So I'm asking for like an instantaneous acceleration right when he slams on the brakes. So yeah, he's slowing down in 8 seconds and something is happening from the time he goes to 65, from 60 to 45. But really what the problem is asking me is how much is he really accelerating or sort of decelerating, I guess, in this case, right when he slams on the brakes. All right, so for this, we want to use our equations. So we'll use n and t axes. And that means we sort of need to define them or maybe draw them on our particular guy at this moment. So let's do that. So here's our Leadfoot Larry. And he has some velocity in this particular direction, 60 miles an hour. And so we know, if we know the direction of the velocity, we know the direction of E hat t. So away we go. So here is E hat t. Just draw it in the direction of velocity, nothing to it. now my normal unit vector points 90 degrees from E hat t towards the center of curvature. So that would be here. So we've got sort of a coordinate system for this problem now, which is nice. And it's sort of riding along the car in this situation. Then our acceleration with our equation that we just saw, at e hat t plus an e hat n, or if we write this out fully, this is the change in the velocity over time in the tangential direction plus the magnitude of the velocity squared over my radius of curvature in the normal direction. Kind of looking at this problem and thinking about each one of these individual terms, I think it's almost pretty straightforward at this point to see each one of these particular terms. So once you sort of have this powerful tool that describes, you know, the accelerations in these e hat t and e hat n directions, it can be very simple to solve these. So here, the change in the velocity over time is constant. We're told that in the problem, it's a constant rate. Slams on the brakes causing the vehicle to slow at a constant rate. It's part of the problem. And I know that I have 60 miles per hour when I start, and 8 seconds later, 45 miles an hour. So this dv dt is pretty simply the change in velocity, 60 minus 45 miles per hour, normalized by the times. So if you want to be clear about this, 0 minus 8 seconds. This is technically the proper setup. So this is like velocity 1 minus velocity 2 divided by time 1 minus time 2. Okay. So this is a change of 15 miles an hour in negative 8 seconds. So you're slowing by 15 miles an hour over 8 seconds. If you do the decimal here, negative 1.875 mile per hour change per second. A little bit disgusting of a unit. I think it's easy to wrap your head around if you've like driven in a car before. How fast is your velocity decreasing every second? I think that's kind of easy to understand. But you know, when we're doing engineering problems, we want to sort of convert. And here we'll have, after converting to feet per second, negative 2.75 feet per second. How many feet in a mile? Incorrect. Yeah, it should be squared. 5,280. I think you got your numbers back there. He said, I think he said 2,580. Okay, that's good. All right, cool. So here we have changing, slowing 2.75 feet per second squared. All right, so there we go. At the time when he first slams on the brakes is what we're interested in. And at that particular snapshot, my velocity is going to be 60 miles an hour. So the magnitude of the velocity, right when he slams on the brakes, 60 miles per hour, which we can convert as 88 feet per second. And we also know our radius of curvature at our track. This is sort of a circular track, or I guess what the snapshot of the radius of curvature of this particular curve is at this time, 2,500 feet. Okay. So finally, after all said and done, my acceleration, I'm ready to go. I have everything. Here is negative 2.75 feet per second squared. in the direction of travel. So this is just the magnitude of the velocity, derivative with respect to time. Adding to this, what is the velocity squared divided by the radius of curvature? So here this will be 88 feet per second squared, normalized by 2,500 feet in the normal direction. So all said and done, negative 2.75 e hat t plus acceleration in the normal is 3.1 e hat n, units here, feet per second squared. That's my full acceleration here. All right, now I want the G-force experienced by my main man, lead foot Larry. G-force. Okay. For the uninitiated, G-force would refer to sort of how many gravitational forces he's experiencing, basically. What is the multiplicative acceleration relative to the acceleration of gravity? Yes, that is correct. So what we're sort of looking for here, let's give it some symbol. Let's call it phi. This is our sort of G-force that we're experiencing. This would be the magnitude of the acceleration normalized by typical gravity, G. We call phi our G-force that he's experiencing. What, you want a different symbol? Oh yeah, English units are dumb. I agree. I got to do it. They forced me. They strong-arm me. We literally have discussions about this at the department meetings. Like people are like, I don't want to teach English units. They're dumb. It's like people say like, how can you argue to like? I agree. We should be off the English system. I think it's silly. Yes, it makes total sense that 5,280 feet are in a mile, and that you need to know that. Complete sense. Except for my sarcasm is, glowing here. Metric units, so dumb. All right. Magnitude of the acceleration can be gotten square root of the sum of the squares. You're getting me on a soapbox here. Acceleration of gravity in English units. So here we are. You can calculate that the magnitude of the acceleration in this situation is 4.14 feet per second squared. Normalized by my acceleration of gravity. And so we get the G-forces that he experienced, which we kind of just given an arbitrary symbol here of phi, 0.129. Now the question is this a lot? We're shaking our head no in the classroom. Why not? Right. So we're not even experiencing like twice the amount of gravity. I mean, you have gravity acting downwards into the page, but aside from that, you also have this acceleration in the plane of the sort of curve of the road of 0.129. So this is very little. If you think about some astronauts, they go through like training at like 8 or 9 Gs, and those things, you never see those things that spin around like really fast, and they're contained in that capsule, and then they're like blackout, and they're like barely breathing, and then they're like come to, and they're like, it's pretty awesome. But yeah, this is not a huge issue. So take those curves, baby, as fast as you want. No, I'm just kidding. I'm not advocating for that, especially today. The little slipper out there today. Please don't take a lesson from Leadfoot Larry. All right, I think we'll stop here for today. Talked enough about tangential normal coordinates. You'll see some practice problems related to this. Next time we'll talk about cylindrical components, and that'll wrap up our rotating coordinate frame discussion. Lead foot Larry.